So we talked about a whole collection of, locks, starting from a test and set lock and going through, up to kind of an abortable, lock that will work in a NUMA setting. Now, if you think about the MCS lock, right? I said this lock is essentially a great lock for a NUMA environment because what it really does is it takes care of the issue of spinning so that I only spin locally. But the question that I kind of want to ask is really, is MCS really a good fit with the requirements of a NUMA environment? Okay? And so here's what I'd like to show you. So imagine that I have a constellation of this form. Okay? So what I have is I have two kind of nodes, okay? And these nodes, and now this could be cache coherent, it could be not cache coherent. I'm not even dealing with the issue of whether this is a cache coherent machine or not. But in this node I have this machine I have two nodes, okay? And in each node I have 8 cores. Okay? So this would be a typical setup of a modern multiprocessor machine. And imagine that I want to design a locking scheme for this kind of a machine. Okay? So what is this locking scheme? So I have a lock, let's say it's an MCS lock, okay, which is a NUMA lock. It's going to be very efficient in terms of the, in terms of utilizing the cache. And in my critical section, as the program runs, I access a whole bunch of memory locations, okay? I'm touching a lot of memory locations. Now, what's going to happen when I run this, program, okay? So when I start running it, and let's say that this thread is the one, this processor is the one that's running, okay? Then, control of these memory locations is going to move essentially into the, into the cache of this node, right? So this is what typically a cache coherence protocol will do. It'll move, the things that are being accessed right now into the cache of the guy, whoever's working on it, and typically it'll be exclusive even. Okay? Okay, so now, this red guy is working on the memory locations, right? And let's say that, now, after a while, some thread on another node starts working on them. So he grabs the critical section with an MCS lock, that's fine, right? But what will happen now is that, all these memory locations will now move over to this other node. Okay? And again, if it goes to node, if control goes to node 1, then again here, and so on and so forth. So even if the MCS lock itself, okay, is actually efficient in terms of where, in terms of where it, the thread spins, the actual memory locations within the critical section are going to be continuously thrashing from one node to the next, okay? And this is a heavy cost on the communication protocol, okay? So really the question here, right, is it really a good idea, okay, to be fair? So, right, the MCS lock is first come, first serve. What do I mean by that? I mean that when a thread accesses the tail pointer of the MCS lock and performs the swap, right, that first thing determines the order in which you get to access the critical section. And I'm asking, right, is this really a good idea in a NUMA setting? Okay? And what do you guys think? Fairness is bad. Everybody agree? How many people think that fairness is good in a NUMA setting? First come, first serve. How many people think first come, first serve is a good thing in a NUMA setting? Don't be shy. Okay, I guess I scared you. There's only one brave guy over there. That's it, right. Okay, good. So indeed, it's not a great idea. So you know, we really want to try to match the, you know, the access pattern to the actual, you know, layout of my machine. So one approach, okay, is this idea of hierarchical backoff. So I do a backoff protocol, okay, and here's what I do. I have, you know, I have a global test and set lock, okay, and I make this lock a backoff lock, but now I don't make the backoff the same on all the nodes, okay? So whoever owns the lock, whoever is on the node that owns the lock, okay, backs off less. Imagine that when I access the backoff lock, I write which node I'm coming from, okay? And if, you know, if I am some thread on this node and I see that the lock is owned by my node, okay, then I access it, you know, I try to do a backoff of a smaller amount than if I were on a node that doesn't own the lock. Okay, you understand the idea? Okay, and so unfairness here is the key to performance. What's going to happen is, right, because the guys from the same node have less of a backoff delay, their chances of getting the lock are going to be higher, and my chances of causing the cache lines to move from one node to the next, which is very expensive, is going to go down. Okay? So the advantage of a hierarchical backoff is it's a very simple idea. It improves locality because now the guys from the same node have a better chance of accessing the data. The cache lines will be local. The disadvantage is, you know, I have to tune this again, like all the backoff protocols, to the platform. It's unstable, okay, in the software sense, okay, because I continuously, you know, as I move it, okay, I have to update it all the time. I don't get a lot of fairness, of course. That's hard to do if I'm trying to be specifically unfair, and we get a kind of, you know, I still get a lot of threads accessing the same global variable. So if before I had built myself into a situation with the MCS lock where I really have threads handing each other the lock control, now I'm back to the scheme where whenever somebody releases the lock, everybody tries to access, and they're all competing for the same global resource, so I get a lot of traffic. So this is not going to, even if I had perfect, if I could perfectly guess who to run at what time, I'm not going to get as beautiful a performance as with an MCS lock. Okay? So people came up to solve this with a protocol which is a hierarchical CLH lock. Okay? And the hierarchical CLH lock works as follows. So, so the idea is I'm going to keep a kind of a CLH local queue, okay, here, and another CLH local queue in this node, okay? So what is a CLH local queue? It's essentially a sequence of kind of implicit pointers, okay? And what I'm going to do is I'm going to have a global tail for the whole thing, and every time whoever is at the head of this local queue will splice into the global queue the whole sequence of things that it has. So instead of doing this individually, I'm going to splice the whole sequence at one time. Okay? And so you see this thing here where the global tail is pointing here, this points here, and so on and so forth. And there's a protocol for that. This is the HCLH protocol. Okay? So each thread spins on a cached copy of the predecessor's node. So I get a lot of the advantages of this kind of a Q-lock style, right? So locally, I have a Q-lock order, but globally, right, I'm going to have the order of the queue based on the order between these nodes. And each thread, as I said, will splice this into the global queue. So if you look at the performance of this, okay, so this is performance of the hierarchy, as I go from 1 to 256 threads, okay, I am accessing 4 cache lines. So in this experiment that I'm showing you here, in the critical section, I have 4 cache lines that I'm accessing. These are the ones that I'm checking to see how much they thrash around. Okay? And I'm measuring throughput. Okay, so as you know, higher is better. This is the hierarchical Backoff lock. Okay, this is its performance. And then this will be the HCLH. So you can see that having HCLH improves the overall throughput of this lock. Okay? Sorry? Nodes meaning, so what I'm saying is I have a critical section, right? And let's say for the experiment, I have 4 counters inside the critical section and I just increment them. So that's 4 counters, each one sitting on a different cache line. Nodes in the machine? No. Oh, in this thing. I don't remember. I don't remember. I'm sorry. From the curve, if I had to guess, well, I'm not going to guess. I don't remember. I don't remember. Okay, so advantages of the HCLH lock: improved locality, local spinning, and it's fair. Well, fair inside the node. The disadvantages: it really has very complex code. It's hard to get long sequences unless you have a lot of contention. So it performs better than the hierarchical Backoff lock. It's more stable, but it's still not a good solution. So surprisingly, instead of getting more and more complex, there's actually a really kind of what I would call a stupid solution, okay, to this problem of getting locality of the cache lines, and I'm going to show you this, okay? And so the solution is called lock cohorting, okay? And lock cohorting works as follows, okay? So this is going to be a general technique for converting any kind of lock into a NUMA lock, okay? And I can combine all kinds of different locks to do this, okay? But I will need a certain set of properties from these locks, okay? So how does lock cohorting work? Okay, and please ask questions. I said it's a stupid protocol, but well, it's not that simple. Okay, so let's just understand the basic idea. So here's what I'm going to do. Okay, what I'm going to do is I am going to have one global lock, and then I'm going to have a local lock for every node. Okay? And I'm going to acquire the locks in the following way. Okay? What I'm going to do is this. If a thread wants to access and get the lock, it grabs its local lock, then it goes to the global lock, grabs the global lock, goes into the critical section. Okay? Does what it does in the critical section, then okay, when it releases the lock, okay, now it's done with the critical section, it wants to release the lock, okay, it checks to see whether or not there's any other threads waiting for its local lock, okay? And if there are other threads waiting for its local lock, okay, then what it'll do, okay, so we call this a non-empty cohort, okay? A cohort, right, is all the guys that I'm waiting with together in my local node. So if my cohort is not empty, okay, then what I'm going to do is I'm only going to release the local lock. I'm not going to release the global lock. Okay? So here's what happens. He goes, leaves the global lock locked, goes to the local lock, and releases it. Okay? And after he leaves, right, the lock situation now is as follows. The global lock is taken by virtue of the guy that was here, okay? And the local lock is released. Now, whoever's at the head of this local lock, okay, what he has to do is just acquire the local lock and go into the critical section. Acquires the local lock, goes into the critical section. He doesn't have to touch the global lock. So he's not touching the global lock now. Goes in, does what he has to do, comes out, to release. He doesn't have to release the global lock again. All he does is release the local lock, right, and leaves. And again, the last guy, okay, goes, grabs the local lock, goes into the critical section without touching the global lock, and when he wants to leave now the cohort is empty. Okay? If the cohort is empty, can he still leave by just releasing the local lock? What do you think? Why? Right? So did you hear the point is this, that if he were now to just release the local lock, then the global lock would be stuck here and no one would be here in order to continue to go into the critical section. So he's got to release the global lock and the local lock. Okay? So if the cohort is empty, he releases, the global lock and then the local lock to avoid deadlock. So release the global lock, release the local lock, and leave. And, okay, what happens now? Now, it's a fair competition. Maybe somebody showed up here, but if not, these guys can go on. So now somebody comes from here, acquires the local lock, acquires the global lock, and now these guys get to run. So what I get is a long sequence of threads, all from the same node, accessing the lock. Questions? Yes. How do we avoid starvation? Right. So what do you suggest? Okay, a timeout is a good idea. What else could we do? Yeah? Yeah, allow 5 of them to go in and then switch. Maybe. I don't know. Right? So both are good solutions. So the idea, what both of you are saying is that I have to limit the size of the number of guys I let go from any node before I switch over. I allow other nodes to go in. Yeah? So I'll invent some number like that. And that's what I'll do. Okay. Good. Clear so far? Other questions? Okay. So he goes in the critical section. Now, what do I need in order to build a cohort lock like this? Okay? So one thing I need is this idea of thread obliviousness. Okay? So let's define a lock to be thread oblivious if after being acquired by one thread, it can be released by another. Okay? So I'm going to define a lock is thread oblivious if the guy who grabs the lock is not the guy who releases the lock. Okay, that's a property that I need. Okay? The other property that I need is a property that I'm going to call cohort detection. Okay? And a lock provides cohort detection if you can tell whether any thread is trying to acquire it. Okay? So I know if somebody's trying to acquire the lock. Now, why do I need these two properties? Okay? So here's the thing. Okay? What I'm doing in the lock cohorting is I'm using two levels of locking. My global lock, right, the one that everybody shares, I'm going to have to make that lock thread oblivious. Why? Because one guy from the local cohort is going to be, grabbing it for the first time, acquiring the lock, but the guy that releases the lock is going to be somebody completely different. Okay? So for the global lock, I need thread oblivious. For the local lock, I need cohort detection. I need to be able to know if there are any threads left there, because if there aren't, I have to release the global lock. Okay? So for the local locks, I need the ability to do cohort detection. Good. So the way I can build a cohort lock is the following construction, for example. I can build a cohort lock where the global lock is going to be a Backoff lock, an exponential Backoff lock, and the local locks will be MCS locks. And I want to argue that this kind of a design will provide me the thread obliviousness here and will provide me the cohort detection here. Let's see why. Okay? So, a Backoff lock provides, thread obliviousness essentially by definition, right? Because, what do I care with a Backoff lock? Who grabbed it and who released it, right? There's no list here. There's nothing shared. One guy can grab it, another guy can release it. It's not a problem at all. Everybody agree with that? Right? Yes? Yeah. Good. Now, I claim that the MCS lock, okay, has the property of cohort detection, right? All I need to do to know if there's if there's somebody still in the MCS lock is take a look at the, pointer, right? Do you agree with this, that a thread can tell if there's somebody else in its cohort just by looking to see, right? If there's if there's essentially a successor? Yes? We agree? How do we know? Why do we know in an MCS lock if there's a successor? Right? Because that's what the successor does, right? It points my pointer to it, right? Say it again. So what he said was that the thread also needs to check the tail to know, in order to be sure that there's somebody pointing there. Right? That's what you're saying? You're saying in order to know for sure that there is somebody after me, it's not enough to look at my pointer. Right? I also need to check the tail. Okay. So you are correct, the way I posed the thing. But let's think about this for a second. So, do I really care if I missed? Do I really care if I didn't see somebody? Okay, let's think about this for a second. What is this property that I really want? What I want to know is that if there is a nobody there, then I better not make a mistake and forget to release the global lock. But there could be threads there and I just don't see them, in which case I'll release the global lock. So maybe if I don't look at the tail, right, in the MCS lock, I might, there might be a successor, but I still would release the global lock. So nothing bad is going to happen. So in a sense, this idea of thread, of cohort detection is just a property that I have to have, right, in order to guarantee more progress. But it's okay to miss here. Everybody good on this? Do you understand what I'm saying? Yeah? Okay. So good. So I do a Backoff lock here, I do an MCS lock in the node, okay? And I need to do a little bit of a modification to the MCS lock because I need to be able to say whether or not you need to acquire the local or the global lock. So when a thread leaves the global lock, the critical section, and detects whether or not there is a cohort, the cohort is empty or not, it should go to the lock variable, and it should say there whether the next thread, okay, has to acquire the global lock or not. Okay, so we have to add a bit there. Okay, do we own the global lock or not? So we add a bit to the lock to do that. And with that, okay, with that modification, I've built myself a kind of a cohort lock that allows me to kind of make sure that all these guys in some sequence will get the lock one after the other, and the cache lines won't move to the other guy until we're done here. Okay? So, and of course, as people said, I bound the number of consecutive acquires to kind of control the level of unfairness in the lock. So this lock is what we call the C Backoff MCS, and now I'm showing you another type of lock. Here is another cohort lock. This one has Backoff globally and Backoff locally. Okay? So it has Backoff both locally and globally. Okay, so the Backoff lock is thread oblivious. Is the Backoff lock, does it have the property of cohort detection? Can you do cohort detection on a Backoff lock? You could have an atomic counter to count how many guys are there in the lock. So to do this counter, you would have to do a compare and set on that, or a fetch and add, or something like that. Yeah, that's true. You could. Yes? Right. So, yeah. I think you could get away with it with this. You're right. This is an issue, but I think what he's saying is, if you have a counter, it's kind of an indicator of where you are. Okay. I think you have to increment it when you go in, release, lower it when you go out. There's a simpler solution to this. Okay. You can add, cohort detection in a much more trivial way. And the way you do this is as follows. You just add a memory location to the lock, okay? And what every thread does is it just updates this field, okay, before you try to acquire the local lock. Okay, so when you start the Backoff, you just write there. So maybe multiple threads are overriding one another. I don't care. I'm just indicating that there's somebody. Okay? So I write, and then they know that there's somebody there. And now the thread that releases the lock resets this. Okay? So every time you reset the lock, you erase this. So if there are guys, updating there, then they will, somebody will overwrite this variable. And as long as somebody's overwriting it, I know there's someone there. Okay? So I might miss. It might be the case, right, that the release overwrites somebody that was there and I won't see him, but that's exactly the same story as checking the tail. So okay, so I missed him, so I released the global lock without a good reason. And the whole purpose of this is essentially to save doing the fetch and add and so on and so forth. So you would be right to say, Nir, what are you talking about? This is bullshit. Just update the counter and forget about it. and probably be right. But you could do that. This is actually very efficient. It's just a write and you're done. Okay, so we've turned the Backoff lock, into also a timeout NUMA lock. I'm sorry, the Backoff lock is also by definition a timeout NUMA lock, right? So this Backoff lock, if you want to leave here, right, you can just leave without any worries. Okay, because a Backoff, is trivially abortable. And if you abort, all you have to do is just update the successor exists field. And then you have a kind of a NUMA-aware abortable lock. Okay, so let me say something about more about lock cohorting. What you get is you get great locality, you get low contention on the shared lock. You don't need to tune much if you do something like CBO MCS, and it has whatever properties you give the locks that you're combining, okay? But you do need to tune the fairness parameters, how many threads you wait for. That's dependent on the application, okay? Cool. Here are some numbers. So this is the same graph. Again, I don't know how many physical processors were here. But I'm going to guess it's around 64, just from the graph. So here's what you get. So hierarchical Backoff lock, hierarchical CLH lock. This is CBO. This is CBO MCS, the Cohort Backoff MCS lock. This is CBO BO right here. Okay. So you can see the performance you're getting is pretty good. And in terms of abortable lock cohorting, this is ABO-BO, the abortable Backoff lock, and this is the abortable Backoff CLH timeout lock. So this is a combination of a Backoff lock and a CLH timeout lock. Okay? You can see you can combine these locks in the cohort fashion in order to kind of get an improved lock. And so on a NUMA machine, okay, on a machine with multiple nodes, if you want to implement a lock, this is the right way to do it. And in fact, when you look at all kinds of high-performance applications, okay, especially database applications, then using a cohort lock scheme, okay, on a multiprocessor is a better idea than using a regular MCS lock or a CLH lock. Okay. Questions? Yes. So remember, I hear you, but remember, this performance gain, this is not from the actual reduced overhead of the lock. This is because the cache lines are not moving. So the advantage of using a cohort lock is because what you're avoiding is the thrashing of the cache lines between the nodes. Okay? And what I'm trying to achieve is avoid the thrashing with as low overhead as I can get. And that's what this is showing. It's really showing you, let's look at the one before, it's really showing you that compared to hierarchical Backoff lock and so on and so forth, I'm reducing the overhead and therefore I'm getting better performance. But reducing the overhead is really mostly the overhead of the cache lines bouncing around and not the overhead of the lock itself. Okay. Yes.